So the next topic I want to talk about is how we can model beam splitters mathematically. So as we were looking at this case of frustrated total internal reflection, we saw that there is these kind of coefficients R and T, which could describe the reflectivity and transmittivity of surfaces. And these coefficients can actually in general be complex because there could be a phase whenever you reflect or transmit. So we can think about representing a beam splitter and the actions of a beam splitter as a matrix where we multiply this matrix by a vector or a column, and the column contains information about the incoming light. So this first entry, the top entry in this column, is, in this case, the electric field of the entering light that's entering this beam splitter from the left. And the bottom part of this column, EB, is the electric field of the entering light entering this beam splitter from the top. And now, if we do this matrix multiplication, we'll see that some of the light that enters from the left is going to transmit, and some of it will reflect. And we can also see that some of the light entering from the top is going to transmit, and some of that's going to reflect. And we can actually predict how much that will be by multiplying this out, the matrix and the vector. And in the end, that's going to equal this output vector, EC, where EC is telling you the total electric field of the light that's exiting out of the beam splitter from the bottom, and ED is going to tell you the total electric field light of the light that's exiting to the right. So we can refine this matrix model for this beam splitter a little bit by considering a couple things. So one thing that we can consider is this principle of conservation of energy, which we've been talking about earlier in this presentation. And in order to bring in this principle of conservation of energy, let's remember that the light intensity is going to equal the magnitude of the electric field squared. And the light intensity is related to the energy, so this light intensity is conserved. So what this will result in is an expression where when we square the electric field, the magnitudes of the electric fields that enter into the beam splitter, it has to equal the square sum of the magnitudes of the electric fields that are exiting this beam splitter. So also remember that from the beginning, our big T transmission, this is going to relate to our reflectance and transmission that are written in these lowercase letters by where small t, absolute value of small t squared is going to equal big T transmission, and absolute value of small r squared is going to equal 1 minus this big T transmission. So after you apply all of the relevant constraints, you can rewrite this matrix for the beam splitter according to 4 parameters. So these 4 parameters are some phi 0, which is some overall phase, e to the I phi 0, that multiplies by the entire matrix. You have this mixing angle theta, and what this mixing angle does is it introduces cosine and sine, which kind of helps you to conserve the energy, since we know that cosine squared theta plus sine squared theta is going to be 1. And then we also have phi r and phi t, which will tell you the phases that are associated with reflection and the phases that are associated with transmission for the beam splitter.